Well, we've talked about rectilinear motion or motion in one dimension. Now we're going to talk about curvilinear motion, and we're going to mostly talk about two dimensions, although we could have three-dimensional motion in a curve, but we're going to start with two-dimensional motion. So let's assume that this particle is traveling along this curved path, and it's defined as a position 1 here and position 2 at a different time. You can see that the position has a magnitude, or a distance from the origin, and a direction, or some angle away from the origin. Up here at position 2, it has a different magnitude and a different direction. As you can see that even though this is the distance traveled as it goes along the path, the actual change in position is defined by a straight line between position 1 and position 2. That is delta r. As delta r happens over a particular time, we recognize that the velocity, the average velocity, is the change in position, or delta r, over delta time. Now, as this, if we want to find the instantaneous velocity, this is the average velocity. The instantaneous velocity happens when these two positions get closer and closer together, or the delta time gets closer together. And that's a familiar concept. And so let's imagine what happens if those two vectors get closer together. You can see that delta r looks closer and closer, like it is tangent to the path. And indeed, as delta r goes to 0, or as delta t goes to 0, delta r is exactly tangent to the path. So that's the takeaway from this little piece, is that the velocity is always tangent to the path. There is never a component that is normal or perpendicular to the path for velocity. Velocity is always exactly tangent to the path. All right, and we're going to introduce now a little special shorthand for derivative with respect to time, and we're going to say that the change in position or velocity, the velocity vector dr dt is equal to r dot. And we may use s dot, r dot, whatever, x dot, y dot, a whole bunch of different things when we're talking about velocity in different directions. But the shorthand is the dot when we're talking about the derivative with respect to time. Okay, let's talk about a little more with velocity. So remember that velocity is a vector. It has both magnitude and direction. So to talk a little bit more about how this would work, imagine that we've got a circular path now, and the velocity, or the particle, is traveling along the circular path with constant speed. Constant speed means that the speed is not changing, and so that the length of the velocity vector, or the magnitude of the velocity vector, is going to be a constant. Now, but because velocity is a vector having both magnitude and direction, can we say that the velocity is constant? Well, the answer is no, because since even though the speed is constant, the velocity having magnitude and direction, we can see that the direction is changing. So velocity is definitely changing. When velocity changes, we have a delta v. And if that delta v happens over time, then we have an average acceleration. So acceleration is equal to delta v over t. And we recognize as delta t goes to 0, we're going to have instantaneous acceleration. It's going to be dv dt, and we'll call that v dot or r double dot. But back to our little picture here, if we want to find out what the magnitude and the direction of acceleration are, the change in velocity over time, we can take those two velocity vectors, that one, and put them tail to tail, like I've done here on this little picture. So here's velocity 1, here's velocity 2, and we recognize that the straight line connecting those two endpoints is going to be our change in velocity. And as this delta t goes to 0, you can see that those two are going to get closer to closer, and that means that delta v becomes perpendicular to the actual velocity vectors, which says that there is a perpendicular component of acceleration. And if the acceleration is only due to change in direction, then the acceleration is normal to the path, or perpendicular to the path. Let's look at if the change in velocity is only due to magnitude. So we can we can depict that by having two velocity vectors here. We're going to say at position 1 he's going this speed. Gets up here at position 2, he's going a lot faster. So you can see that there's definitely a delta V, but it's only going in one direction. So if, and it's easy to see in a straight line, you can see that there is a change in velocity, which means we have a delta V, and it is going in the same direction as velocity. Therefore, if the change in velocity is only due to magnitude, that means the acceleration then is going to be parallel to the path or tangent to the path. Same thing, it's going to be along the path. So we have two components of acceleration then. We have a normal component of acceleration due to change in direction, and we have a tangent component due to change in magnitude. And that will always be our case with acceleration. There will be two components to acceleration, one normal to path due to change in direction, and one tangent to path due to change in magnitude. And most of the time, our acceleration is going to be a combination of normal and normal and tangent. And so, in general, A is not going to be tangent to the path like velocity. Okay, I'd like to talk about the coordinate systems that we'll discover in curvilinear motion. We have three coordinate systems we're going to consider, and right now we're going to talk about the rectangular coordinate system. So again, let's talk about this particle traveling along this curved path. If the velocity is tangent to the path, so we draw a tangent line to the path, at any point along the path, the velocity is going to have a different direction, and so but in general, the velocity is always going to be tangent to the path. If it has a magnitude and direction, then we can recognize there, and we're in the xy coordinate system, we can say that there's going to be an x component going along the x-axis and a y component going along the y-axis. So we can say then that in planar 2D space, the velocity in the x direction is going in that direction, and we recognize the velocity in the x direction is equal to the change in position in the x direction over time, or dx dt, or x dot. So in other words, this velocity in the x direction is going to be dx dt, the change in position in the x direction over time. In the y direction, we'll have dy dt, or y dot. Now the magnitude of velocity is going to be given by the Pythagorean theorem. Because this is a right triangle, we're going to know that there's going to be two components, and we can say that the square root of the vx squared plus vy squared is going to be our velocity. So that's going to be the magnitude, will be square root of vx squared plus vy squared. The components of velocity, if we know the magnitude, would then be the vx is going to be v mag times cosine of theta. So it's going to be this component here, the cosine, and vy would be the sine component. And you should remember that from trigonometry and from our work in statics. Okay, acceleration in a similar way. We're going to, as we travel along the path, as we talked about before, we're going to have some acceleration. We may have an x component of acceleration and a y component of acceleration. In this case, however, acceleration is not going to be tangent to the path. As velocity is tangent to the path, acceleration is going to have some other angle, but it's still going to have components in the x direction and in the y direction. And we've talked before then that said that acceleration in the x direction is the change in velocity with respect to time, the velocity in the x direction with respect to time, and we're going to call that x double dot. Acceleration in the y direction is y double dot. The magnitude of acceleration, again, by the square root of the sum of the squares, we have a right triangle, ax squared plus y squared, ay squared, the square root, and then magnitudes of the components are found by the cosine and the sine. So in order to evaluate some of our activity here in the xy coordinate system, we're going to have to remember how to take derivatives. And so let me just remind you that the regular derivative, as I call it, is this is the regular derivative form, d dx of u to the n, and that's going to be n u to the n minus 1 du dx. Now u here could be a function of x, or it could be some other function. But in general, if we're going to take the derivative with respect to x of a function, then we have to say n u to the n minus 1 du dx. If we're going to take the time derivative of this same function, we can say d dt, but then we'll have to take du dt. And here I'm taking du dx here and du dt, and we're going to talk more and more about how to switch from the xy domain and then into the time domain and then back and forth. But generally we do that with the chain rule. And so if you have a function of x, like y, as a function of x, and we want to take the time derivative of that, and we want the time derivative of y, so we want dy dt. In order to take dy dt of a function of x, we have to take the derivative with respect to x, or dy dx, and then multiply it by dx dt. Now, again, this isn't real algebra like this, but you can kind of see the way these two fractions are arranged, that dx kind of almost cancels, and such that dy dt, if those canceled, you'd have dy dt again. But don't think of it as a fraction, because it's not really like that. But doing that, you can make sure that your equations are set up properly. So in other words, to take the time derivative, then you take dy dx and then multiply it by dx dt. If you happen to have a product, you have two terms, and they could be functions of x or functions of time, and you want to take the time derivative of that. Recall that in order to take the time derivative, or the derivative of a product, we use the product rule. We're going to say that u times the derivative of v plus v times the derivative of u. If we're going to take it in the time domain, then we want to take those derivatives in the time domain, or ddt. If these are functions of x, then you have to take the derivative of x first, and then take the derivative, or then multiply it by the derivative of x with respect to time. And we'll do some more examples of that. Okay, so before I talk about these examples, I'm going to come back to that page, but let's look at this little picture, which is again a little parabolic path, and that for any position xy, our equation can define x as a function of y by that equation. So we know that the positions are related. There's only one value of x for every value of y as it goes along the path. X dot and y dot are also related because the particle stays on the path. In other words, there cannot be two values of x dot for a single value of y dot on a path like this. So, and those are determined by taking the time derivative. So let's suggest that if we have a function y equal to 0.2x squared, and we want to find y dot, we can take the time derivative of that equation. So y dot is equal to dy dt, which is equal to dx dt. Oops, that should be dy dx, dx dt. Misprint there. And so let's take the x derivative of our function dy dx. dy dx, if I got a 0.2 and an x squared, that would be 2 times 0.2, or I got 0.2, and then the 2x squared would be 2x. So this part of here is going to be my dy dx, and then I need x dx dt, and that's going to be x dot. And that's how we use the chain rule in dynamics. So multiplying all that out, you get y dot is equal to 0.4x x dot. It's pretty easy. Okay, x double dot and y double dot are also related by the path. In other words, there's only one value of y double dot for any given position, xy, and value of x dot and x double dot. So again, we'll take the time derivative to find out what y double dot is. If we have a function of y dot, then we can take the time derivative of y dot to get y double dot. So let's just do that. In order to do that, we have to recognize that this term here is now a product. In other words, I've got actually three terms. I can combine two terms and make those into one product and do that. So let's do that. Let's call the first part of it my u and the second part of it my v. And so in order to take y double dot, I'll say u times v dot plus v times u dot. That's the product rule. So y double dot, u, 0.4 times x is u. V dot would be the time derivative of x dot, so that's x double dot, plus my v, which is x dot, and then I take the time derivative of 0.4x. Now here, 0.4x is not a function of time, so in order for me to take u dot or the time derivative of 0.4x, I have to take dy dx and then dx dt. So dy dx of 0.4 is equal to, or dy dx of 0.4x is equal to 0.4. Then I have to multiply that by dx dt, and that gives me another x dot. So this is a very familiar thing where we'll have an x double dot and an x dot squared in when we use the product rule. And this is, I call this the product rule plus the chain rule, because this whole thing is called the product rule, but within the product rule right here, to take u dot, we have to use the chain rule. Okay? All right, just a couple more examples. Back to my other page here. This will be in your notes, but here are just a couple more examples of chain rule, product rule working together. Let's just say that y is equal to x cubed. If we want to do y dot, that's pretty easy. Y dot is equal to 3x squared, that's my dy dx, times x dot. And that now becomes, this part becomes my u, and this becomes my v. So y double dot would be u v dot plus v u dot. So this would be my 3x squared right there, plus v dot. So that is the derivative of x dot is x double dot. Plus x dot is my v. And u dot is going to be dy dx of here. So that would be 6x plus, or multiplied by another x dot. And here's another example down here. I think you can probably walk through that. Okay, a couple of other things about what kind of problems we might encounter in this type of behavior. In general, again, the particle does not leave the path. And the path can be a variety of kinds of things. It could be a slot that it doesn't move out of, or it could be a road that it stays on, or it could be a trajectory from a projectile, or a trajectory from a rocket. So several kinds of paths can be described. It can be a flat path, meaning you could be looking straight down on it, and the xy coordinate system could be in this direction and be in the horizontal plane, or it could be in the vertical plane, like this roller coaster. So there's several kinds of paths that can be defined, but in all cases, we'll have an x and a y with a fixed origin that we'll be using to analyze and take derivatives and to find x dot, or to find y dot and y double dot. Okay, I'd like to do a couple of problems with you. Here's a fundamental problem, and what's happening here is this box is sliding down this path and is going in this direction, and as the values are given here, it says that the equation, or the definition of the path, is defined by this equation of 0.05x squared. It says that the x components of velocity and acceleration are -3 meters per second in the x direction. So it says that it has -3 in that direction. And we know that the actual velocity is tangent to the path, don't we? So we know that the velocity is actually going, the actual velocity is going this way, but this is going to be Vx looking like that. If there's a Vx going in that direction, and there's a tangent component, or tangent component here, we know that there's a Vy going in that direction. So I'll just sketch those in on my particle so you can see the actual directions. And the question is, oh, and then there's also an acceleration. It says that it is -1.5. Now again, our directions are that x goes this way and y goes that way. So that's going to be my positive direction going that way, positive that way. So when it says that Vx is negative, it's going in the negative direction, meaning opposite of positive. Acceleration is going to be -1.5, which means that it's accelerating in that direction. And that kind of makes sense. As the box slides down the hill, there's going to be some acceleration, so it's going to be accelerating in the x direction, in the negative x direction, back toward the origin as it moves down the hill. All right, so the question is, determine the y components of velocity and acceleration of the box at this instant. Well, there's a couple ways we can approach this problem. First is we can find the velocity components using the slope method. So let's look at that. The velocity, or the position, is defined by our equation. And if we want to find the slope of the equation at any point, we take the first derivative. So that would be dy dx. If I take dy dx of that equation, I get 0.1x evaluated at x equals 5, because that's where our position is, and I can see that at x equals 5, plugging that in there, dy dx is 0.5. We recognize dy dx is the slope, which is equal to the tangent of theta. You should remember that from other work. So let's draw a little picture of how that looks then. We have a velocity going this direction, we have a velocity in the y direction, and a velocity in the x direction with a theta in between. We know that tangent theta, or then we can find theta by taking the inverse tangent and find out that angle is 26.56 degrees. Now we can find out the components of that. We know that Vx is going to be 3, or negative 3, and we know that Vx is equal to V cosine of theta. So I'm going to say that V is going to be equal to negative, I should probably put a negative in there and make that a negative as well. And we can say that the velocity is going negative 3.354. That's the actual velocity. The velocity in the y direction, that component, is going to be v sine theta. And so I've just solved for v. We got the sine from before, and I can say that v in the y direction is going to be negative 1.5. You can plug those numbers in your calculator and troubleshoot my math there. Another way of doing that, this equation, or this problem, is to use the chain rule and the product rule. So again, we've got a velocity coming down the hill. Those are given as before. If I want to find out the components of velocity and acceleration, and we're looking for the y components, I can use the chain rule and the product rule. So y is equal to 0.05 x squared. Y dot is, taking the time derivative of both sides, I got 0.05, that would be 2x, this is going to be my dy dx, times dx dt. Multiplying that out and evaluating that at x is equal to 5 and x dot is equal to minus 3, I can see Vy is equal to negative 1.5. So the chain rule works really fast. The slope method is also very good in visualizing what's going on. But the chain rule works very quickly often to try to find the y components. To find the y component of acceleration, we'll have to take the derivative of this equation. Again, I'll actually just use this form right here. So I'm going to call this my u and this my v. So I'm going to say that that's going to be equal to 0.1x times x double dot plus x dot times dy dx of this, so that's 0.1, and then I have another x dot, as we did before. Multiplying all those out and evaluating them at x equals 5 and vx is equal to minus 3, I can see that my acceleration in the y direction is 0.15. Now, with the slope method, we could only get as far as velocity. We couldn't use the slope method to find the acceleration. So if the question is asking for acceleration, you're going to have to walk through all the pieces here. You're going to have to go through the chain rule to get to y dot, and then the chain rule plus product rule to get to y double dot. All right, the last problem I wanted to visit with you about, here's another fundamental problem. And here we have a particle that's traveling along this path, and it's being forced along this path by this slider. This little collar is moving in this direction along this fixed bar. It's got this slot thing, and there's going to be a little slider kind of thing that's here, so such that as this moves like this, the particle moves up and travels along this path. The x behavior is defined in the problem as a function of time, so that whatever happens in the x direction down here is going to be the same thing that happens in the x direction up there, because those are all constrained. Okay, so our question is determine the velocity and acceleration when t is equal to 0.5. All right, let's notice something here. We can build a little table and say that x is equal to, here's our definition, x is equal to 4t to the fourth, and we're looking for what happens at t is equal to 0.5 seconds. So I can evaluate x is equal to 4t to the fourth and evaluate that at 0.5, and let's call that 0.25. To find out x dot, I just take the derivative of that, and that's 4 times 4, 16t cubed, evaluating that at 0.5, and x double dot, take the derivative again, 48t squared, and at 0.5 is 12. All right, so that gives me the components of speed in the x direction, x dot, and acceleration in the x direction, x double dot. Y is given as a function of x. in our equation is given as a function of x. But we can easily make that into a function of time by substituting this x of 4t into that x there. So I can say that y squared, right up here, let's see right there, y squared is equal to 4x, y squared is equal to 4x, and by substituting my definition of x given in the first part of the problem, I can say that that's equal to 4 times 4t to the fourth equals 16t to the fourth. Now that I have that, I can take the square root of both sides. That's kind of conveniently arranged here. But I take the square root of y squared, I get y. Square root of 16t to the fourth, I get 4t squared. Now I have y as a simple function of time. Taking dy dt as y dot, dx dy, taking y double dot again, and then I get, and then evaluating those at t is equal to 0.5, I get those numbers, and so that makes it really, really easy. To find out the magnitudes, and that's what we're looking for, the velocity and acceleration magnitudes, we take the square root of the sum of the squares. So velocity, I take the square root of vx squared plus vy squared. Vx squared is 2, vy squared is 4. And I take the square root of that, I get 4.47. Acceleration is going to be the square root of x double dot plus the square root, or plus y double dot, square root of each of those, and so that would be 12 squared plus 8 squared. Square root is going to be 14.4. Alright, so that's pretty easy when x is given as a function of time. It's nice and easy to plug those things in there. If we wanted to, or if we needed to, we can also do this with the chain rule and the product rule. In this case, it's a little bit more difficult to do the chain rule and the product rule, but let's go ahead and do that anyway. And from our before analysis, we know that these are the values given for x and y at t equals 5 and x dot. So I'm not going to redo those. Let's just focus primarily on y dot and y double dot. So y squared is given to 4x. Y, I can take the square root of both sides here, and that gives y is equal to 2x to the 1/2. I can take the time derivative of this equation, y is equal to dy dt, which is equal to dy dx, dx dt. So I'll say that that's 2, and then I take dy dx here, I'll take that 1/2 times x to the minus 1/2, that's what that is. Then the dx dt is x dot, so now I have an expression for y dot. And simplified that just a little bit, I'll get y dot is equal to x to the minus 1/2 times x dot. Evaluating that at t is equal to 0.5, I get y dot is equal to 4, which is agrees with what we had on the other page. To find y double dot, I'll take this equation, y dot is equal to x to the minus 1/2 x dot, and then I'll have to, since that's now a product, I'll have to use the product rule. So I'll call this piece my u, and this piece my v, and so I'll say that this is x to the 1/2 times dx or ddt of this part, so that's x double dot, plus x dot, and then the dx dt, or ddt of this part, so that would be minus 1/2 comes in front, x to the minus 3/2, and then I always have another x dot. Combining all these things and then plugging in the values of t is equal, or of what we had for x dot and x, we can see that y double dot is equal to 8, which again matches the previous page. So we get the same answer doing either way. In this case, this was a little bit more work, but often this is going to be necessary because we don't often have x is given as a function of time, which makes that substitute very easy.